Here we go. We're going to talk about protons, electrons, and neutrons today. So we have these atoms. They're the building block of life. We're showing you the Bohr model over here just because that one's the one like a solar system. So this is the easiest one for help us to map it and understand what's going on. The protons are positive charged and they're located in the nucleus. So this one has 1, 2, 3, 4, 5, 6 protons, which makes sense because it is carbon, and we'll show later on the periodic table that carbon has an atomic number of 6 and 6 protons. And how many electrons does he have? Those are the blue ones. They're found in the cloud. And there are 1, 2, 3, 4, 5, 6 electrons in this carbon. So we had 6 protons and 6 electrons. Protons are positively charged. Electrons are negatively charged. So this whole thing is an uncharged particle or an atom. Now, the neutrons in there are also in the nucleus. So the protons and the neutrons are in the nucleus in the center, where the electrons revolve around. We just know now it's not as pretty as how we picture a solar system. It's a little bit fancier than that. When I count my neutrons, 1, 2, 3, 4, 5, 6, 7. We have 7 neutrons. So 7 neutrons and 6 protons make up our nucleus. And our nucleus is a total of 13. This is where the mass is centered in our nucleus because the electrons have very, very, very little mass. So when we call something carbon-13, that is always the mass. So when you are naming an element, you are always going to use its mass to help you name it. You can also see it in the upper left-hand corner or left superscript as well. Carbon's symbol, carbon's chemical symbol is an uppercase C. So you always want to follow those nomenclatures there. So that's carbon-13. You could actually have it a little bit more detailed. So while this is stacked isotope notation with the symbol and the mass, we could have more information written there. So traditionally, you're going to see carbon-13 with this nuclear notation. In the A spot, that is where you put the atomic mass. The Z spot is where you put the atomic number, which is also called the nuclear charge, which is also the number of protons. And the CH over here is the charge. Notice we have an uncharged atom. So we are going to have 0 for the charge. What's our mass? The mass is always in the name, 13, unless it's the same mass as the periodic table. And the Z is the protons. So that is 6. So you would write its atomic notation like that. Now, right now, I did not show the 0 because I tend to be lazy, so do all chemists. So we tend not to show the 0. We only show it if there is actually a positive charge or a negative charge on it. So that is how you would make those stacked isotope notation from a picture of an atom so that you can look at that model. This Bohr model still works pretty well for identifying the location and the charge of your subatomic particles. The carbon on the periodic table is carbon-12, so that one we often just call carbon. Carbon-12 and carbon-13 are 2 different isotopes of carbon. Isotopes, iso, when we break that down, means same, and the P in the topes is to remember same protons. So carbon-13 has 6 protons, carbon-12 has 6 protons, carbon-14 has 6 protons, but they have different amount of neutrons, so they have a different mass. Their identity is tied to the number of neutrons. That's why that's the atomic number. So you state the name with the mass, like we did up here, and you identify with the atomic number. And we'll do some more of those again on the periodic table later. So here we have a set of equations that hopefully you have in your notes. You will have to memorize them so you know both the key terms and also how to find things. So what is the stacked isotope or nuclear notation for the sodium-25 atom? So atom means it's uncharged. So now I know my charge is going to be 0. I need to figure out the atomic mass, which is what A is. A down here is the atomic mass. And I need to figure out the number of protons. The number of protons is also capital Z, and it is the atomic number. So if I look on the periodic table, I find that sodium has an atomic number of 11. And its atomic mass, we do not use the periodic table. Why? When you state the name, you use the mass. So the mass value is 25. So that would be the stacked isotope notation of the sodium ion, or sodium atom, sorry. And now down here, what if they just give us the number of protons, electrons, and neutrons? We need to calculate it. Atomic mass. What's the formula? Protons plus neutrons. 11 plus 10. So my atomic mass is 11, or 21, 11 plus 10. And our atomic number goes by the number of protons. So that is 11. Hey, that's the same number of protons as up here. So right now I know that's sodium. Otherwise, I could just look on the periodic table to find number 11, and that would give me sodium. You say the name with the mass, you identify it by its number of protons, because in isotopes, the protons are the only thing that stays the same. Isotope, same protons. What about the charge? Oh, we got a different one here. Do I have an equation to find the charge? Yes, I do. And charge is just a simplification of the ion charge. And so protons minus the electrons. 10 minus 11 is 1. Here's a change. You add a positive number at the end if it's a positive number. If we had done it the other way around and we had 10 protons and 11 neutrons, 10 minus 11 would be -1. And then we just place that 1 on the right side when we are doing this in chemistry to show that it is a charge of 1 minus. But our charge was 11 minus 10. So we have a positive 1 charge. And so there is the stacked isotope notation, just a little bit prettier. Okay. If you do not have the charge here, it is all wrong. So that's a difference from math class. When you see the charge of an ion, you need to show either the positive or the negative value right there. Okay, so make sure you have all of those equations written down. Okay. This bottom isotope, we call the name with the mass. So the name of this guy is sodium-21, but we ID it because on the periodic table, he's number 11. Number 11 is always sodium. 11 protons is always sodium. If we lose a proton, then it's not sodium anymore. Then it would be neon. Okay, so the identity always goes with the number of protons, and the name goes with the mass. All right, so now look at those mass values that are on the periodic table. Those are actually called the average atomic mass. They are not whole numbers, and that is because it takes a weighted average, kind of like how your GPA is calculated, to figure it out. So boron 10, the isotope boron 10, same proton. So boron always has 5 protons, but in this case, he has 5 neutrons. And we have boron 11, always 5 protons, but in this case, different neutrons. When you have different amount of neutrons, you have a different mass, because the mass is equal to the protons and the neutrons. So we have 2 isotopes of boron, boron 10 and boron 11. But boron 11 happens more. So we are closer to 11 than 10. Just like on your GPA, if you have all A's and B's, but you have more B's, you're closer to the 3.0 than the 4.0. It's weighted average. And that's why these are not whole numbers. So we can actually calculate that. This is the formula. That this weird little s, that is the sigma. That means sum in Greek. It's the Greek letter sigma, and we use it for sum. And we take the sum of the decimal abundances times their atomic masses. So if you've never done that before, if I have 5 elements, then I would take the decimal abundance times the mass of element 1, and then I'd take the decimal abundance times the mass of element 2, decimal abundance times the mass of element isotope 3, decimal abundance times the mass of isotope 4, decimal abundance times the mass of isotope 5, and then I would add it up to get the average atomic mass. These are going to be, 5 isotopes, same protons, different number of neutrons. Okay, so that we can figure out the mass value on the periodic table. So sometimes you'll be asked to calculate the mass value on the periodic table. Now, some of you are going, oh, I can just say, if they ask for what is the average atomic mass of carbon, I am just going to say 12.01, because that is what my periodic table says. Your periodic table is often not accurate enough. So it should be close to 12.01, but it may be off by a little bit. So always do the calculation, because when they have you do these problems on the SOL, they pick ones that don't match so that you recognize you have to do the math. So what do we have here? Carbon has 3 isotopes. Carbon 12, its name shows its mass, 6 protons and 6 neutrons. That one's considered stable and not radioactive. And then we have carbon 13 and carbon 14, which are radioactive, which means they decay. They are unstable. They're a little wobbly top because they are not in a nice, perfect combination. So those guys do not stay around as long. Now, they take a long time to decay, like 6,000 years, to have their mass go in half, but they're not like strong carbon 12 building block of life strong. All right, and so on here, we have the isotopes, carbon 12, carbon 13, carbon 14, carbon 12, 6 protons, 6 neutrons, carbon 13, 6 protons, 7 neutrons, carbon 14, 6 protons, 8 neutrons. See how lopsided it's getting? That one occurs only in really trace or really small amounts. So that is how you can vary it, but they all have 6 protons, because they are isotopes, same protons, different neutrons, different masses. Right, so our abundance is how much they're found in nature. So you take a whole big pile of carbon and then you analyze it to see how much is carbon 12, how much is carbon 13, how much is carbon 14. You may have heard of carbon 14 because that is what people use when they are doing radioactive dating or carbon dating. Okay, they're looking at the radioactive decay to figure out what is going on in that guy, because he's around for almost 6,000 years. It's just a really good one to measure and see how much he's changed, to figure out how old something is. So why didn't I give the abundance of carbon 14? It's in trace amounts. Can I calculate it? I can. We have a total of 100%. So I'm going to subtract carbon 12 and carbon 13's percentage from 100%. Now I know carbon's percent. So don't freak out if they don't give you all the abundances. Finding the missing percent abundance first, and then find the average atomic mass. Sometimes they won't even say this. They'll just say, what is the average atomic mass? Make sure you go through the whole calculation. Find the missing percent abundance first if they're not all given, and then go on. The decimal abundance is the percent abundance divided by 100. It's just changing it from a percent to a decimal. So we're just dividing by 100. 98.89% is 0.9889, and so forth. Now the weighted mass calculation, that is what we said, the sum of the mass times the decimal abundance. So right now we're getting the mass times the decimal abundance. So the mass times the decimal abundance. is what would go on those next column. 12 times 0.9889, 13 times 0.01109, 14 times 0.00001. And we're finding those answers. Those are their weighted masses. Carbon 12 has a mass on the sample of 11.8668. And now this is where the sum comes in. After you find the weighted masses, then we sum those guys up and we get 12.0111. So our average atomic mass, which is very similar to what's on the periodic table, is what we found in this calculation. So here's that periodic table that hopefully you have a printout of. This is the one you will get in the SOL, or if it's updated, hopefully at some point they update it. Because as we synthesize or create new elements, we are actually have already filled in a lot of this chart down here. So at some point it will be updated. But what's nice about this periodic table of element chart, it tells you the atomic mass is the one in the upper corner. So you can always go look for the atomic mass right there. Okay. The name, they give you the name with the element. That is also a nice plus. AP and IB, you don't get the name, so you'll have to have it memorized by then. The atomic number, what else is that? The number of protons, the identity of the atom, the nuclear charge. And those are those numbers. Hey, when you look at this, look, there's a pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The periodic table is arranged in increasing atomic numbers. Okay, and so they figured out a really nice balance here so that all of the noble gases ended up in one column. These guys tend to be gases at room temperature. So they have a lot of similar properties. Every group or family has similar properties. Oh, wait, group or family, what's that? Let's look. Group 1. This is group 2. What is common? Group 1 is column 1. Group 2 is column 2. Group 3, column 3, and so on. If we're talking about periods, period 1 is row 1. Period 2 is row 2. So when we say the periodic table of elements, it isn't a fancy name. It just means the rows of the elements. We just were lucky that Mendeleev and others worked to get it organized so that every group or family, just like your group or family, there are some traits you share. Not all of them, but some of them that you share. And so that's a consistent thing to remember. When you're in the same group, you have a lot of the same physical and chemical properties. Not always, okay, but you tend to share some properties here. Okay, so for group 1, when exposed to water, as you go down, they have more and more violent reactions with water. So that's one of those types of properties there that the groups share. Okay, so what else can we look at it when we are looking at those similar properties? The other things that we have on here is group 1. If we were to draw all of group 1s like carbon was at the beginning, we will notice it has 1 valence electron. That means 1 electron in the outer row. That is what is contributing to how it bonds, how it matches up with other things, and those properties. So everybody in group 1 has 1 valence electron, similar properties. Now, sometimes, so let me put those valence electrons on here. So those are those valence electrons. So everybody in group 13 has 3 valence electrons. Okay. Group 18, that's the noble gases. These guys have 8 valence electrons, but helium only has 2 electrons total. Okay, because he has 2 protons and he needs 2 electrons to balance to be an uncharged atom. So he doesn't have 8 valence electrons only because he doesn't have 8. But he doesn't fit over here as helium because he does not share properties with these guys. He's not a metal. Okay, he does not share properties with those alkaline earth metals. Okay, so they shifted him over to where the noble gas was. So those are those valence electrons helping us figure out properties. And then we have those charges on the bottom. Okay, so when they're in their charge state, they're ions. If they're positive ions, they're cations. Those are the green ones. Okay, if they're negative ions, they're anions. And that's all about what they have to do. One valence electron. If we lose one electron, we become more positive. Why? Electrons are negative. So in group 2, we have 2 valence electrons, and if we lose 2 negatives, then we have 2 extra positives, because we want to become like a noble gas and have only 8 valence electrons, except hydrogen and helium can only have 2. Now there's a weird area in here. Why didn't I talk about 3 through 12? Because those guys are transition metals, so their charges change. And so you'll have to use Roman numerals with them, but that's another lesson. And just remember, green are the cations, and that does include group 1 and group 2 over here. Those are also positive. And then those negatively charged areas, those negatively charged areas, those guys are the anions. Right? Okay, those guys over in red are typically the non-metals, and the ones in green are typically the metals. So groups share similar properties. And just remember what you will get. You will not get the shaded in areas. You will not get the valence electrons or charges. So either memorize it or understand how the pattern is so you can recreate the pattern. You will have this little staircase here. If it's touching the staircase, you can assume that it's a metalloid. There is a lot of debate about if it actually is. And then the metal side is over here. The metals are typically positive. The non-metals are typically negative or anions, except for our noble gases, who are perfect with a 0 charge. And that's all.